So drivers and constraint. Continue chapter 7. Drivers of page 154. So erosion control is therefore strongly influenced by the factors that encourage or discourage farmers from adopting soil conservation. In non-agricultural areas, erosion is important wherever it threatens the integrity of a resource. The driver for erosion control is to protect the resource and prevent the ability for little damage, particularly in society that adopt the principle of the polluter pays. Moreover, organization like Highways Agency engineering companies, pipeline companies will install protective measure because they want to retain their vision for sensitive management of the environment. So the first driver is perception of erosion. So the relevance of conservation measure to a farming system depends in part of how farmers and others perceive the erosion problem and its consequences. Most farmers are aware of the problem it affects, and the notion of the peasant farmers damaging land through erosion is severely mistaken. It's actually the small scale farmers is much experienced and efficient practitioner of land husbandry. Compared to large-scale commercial farmers, but with a different objective, namely that of survival rather than profit. So most farmers, are concerned with the effect of erosion on productivity and on increased cost of seed or replanting a crop destroyed by erosion. Fertilizers to maintain soil fertility and water storage or irrigation facility to provide additional water for crop growth. Farmers' decisions, however, tend to be a compromise between preventing long-term soil damage by erosion and maximizing short-term income. Generally, the farmer is not willing to change practice, but will do so if substantial benefit arises and the investment cost can be recovered. Where a land user do not perceive such benefits, soil conservation is unlikely to be adopted. For example, where land is cheap and readily available, the incentive is to make a rapid profit and then move on to new land when the soil becomes unproductive. For the subsistence farmer, a particular problem is whether or not a new practice increases the risk of crop failure. Taking up higher yielding property that may also have to reduce erosion by increasing biomass will not be an acceptable gamble. If in 1 year out of 10 the crop yield less than the minimum required for subsistence, even though much higher yield will be obtained in the other lands. Okay, this is just the reason for the perception of erosion. The second driver is land tenure. The arrangement by which tenure is granted to the land user can influence attitude towards soil conservation. So where farmers on the land, they are more likely to consider the long-term consequences of their action and adopt soil protection measure unless the need for short-term survival dictate otherwise. So tenure system based on short-term cultivation rights, sharecropping, collective generally lead to poor management because of uncertainty about whether conservation work carried out on the land will be rewarded. The third one is labor. So all soil conservation work implies extra labor, of course. To construct the terrace, you see here, contour terrace require 100 to 300 person days per hectare. 1 year, almost 1 year to construct the contour terrace. It is needed for the building building maintenance of the terrace and for the growing of the additional soil protective crop either in rotation or by intercropping. The likelihood of any soil conservation measure being adopted depends on whether the farmers and associated family can meet the increased labor demand. You see the table 7.2 here. Labor demand, the availability of labor can be improved if farmers have sufficient income to hire additional workers, but more often than not, serious constraint exists, particularly at time of land preparation and harvest when the work has to be done in a very short time. Other ways of improving labor supply are through communal scheme where farmers and their families come together to build terrace, dig the soil with the crop for what is at the same time efficient application. So in the book, you can read through access to, there are other factors or other drivers for soil erosion control, access to soil conservation, external factors, technological transfer, economic evaluation. This is approaches to soil conservation, page 161. So approaches to soil conservation, it's based on type of the land. So in this book, they are cultivated land, grazing land, or non-cultivated land, forest land, land clearance, mining land, rough land, many. But focus in my slide focus on two cultivated land and grazing land. So this is either cultivated and non-cultivated. So cultivated land erosion is exacerbated by attempting to farm slope that are too steep. Cultivating up and downhill, continuous use of the land for the same crop without fallow or rotation, inadequate use of fertilizer and organic manure, compaction of the soil through the use of heavy machinery, and pulverization of the soil when trying to create a seedbed. The soil conservation relies strongly on agronomic method for cultivated land, combined with sound soil management with mechanical measure playing only a supporting role. So for cultivated land, the best soil conservation is agronomic measure. So cultivated land, there are three mechanical method: soil management, agronomic measure. Agronomic measure, there are mulching and crop management. So for crop management, cover cropping, strip cropping, crop rotation. For mulching, two natural and synthetic. Yeah, can refer to figure 7.1, the strategies to conserve soil for cultivated land. It's different from grazing land under the non-cultivated land. Erosion this one is page 162. So erosion problem arises when the protective cover of range land vegetation is removed through overgrazing. Erosion control depends largely on the use of agronomic measure. Figure 7.3, that's figure. For soil conservation strategy for non-cultivated land, these are directed at determining and maintaining suitable stocking rate, although this can be difficult, if not impossible, in areas where people attach cultural and social value to the size of their herd and at planting erosion-resistant grasses and shrubs. So for non-cultivated land, there are two: agronomic plus and soil management and mechanical method. So for agronomic and soil management, there are two: forest land and grazing land. So for grazing land, to conserve it, they need to plant grasses and planting shrub and control the grazing. For forest land, they're planting trees and agroforestry. For rough land, is planting trees, shrub and grasses. Hydroseeding, chicken engineering is watering and sticking and brushing it. For this slide, I only focus on grazing land. For forest and rough land, we can refer to page 165 and 168. So traditional grazing systems are often well adapted to the local condition of climate, soil, and vegetation, making use of traditional grazing on a nomadic basis. So virtually all traditional grazing systems are under pressure today. The first, human population numbers as a result of better herd livestock numbers as a result of better veterinary service are both increasing. Second, there is a conflict between individual and family ownership of livestock and communal ownership of the pasture. The individual derives a positive utility of almost one for every additional animal on and graze on communal land, but experience a negative utility of only a small fraction of one as a result of consuming overgrazing. There are method, a tradition in Turkana in Kenya have a careful control and reasonably flexible system administered by the elders. Cattle are grazed in the lowland immediately after wet season, taking advantage of the annual flush of rain, and then move to slightly wetter hill areas during the dry season, toward the end of which they are kept around a permanent home state in riverine woodland from which dry season forage can be obtained. Modeling the soil erosion. So for modeling the soil erosion, you can refer chapter 6 in PC Morgan. Okay, this one is page 116. It is not possible to take measurement at every point in the landscape. It also takes time to build up a sufficient database to ensure that the measurements are not biased by an extreme event or a few years of abnormally high rainfall. Long period measurements are required to study how erosion rate respond to changes in land use, climate, or the use of erosion control measures. So in order to overcome this deficiency, model can be used to predict erosion under a wide range of conditions. The result of the prediction can then be compared with the measurement to ensure their validity. Most of the models used in soil erosion studies are of the empirical grey box type. This is type of the model. So under type of the type of model, physical, analog, digital. So under empirical, there are three types: black box, red box, white box. So black box, the only main input and output are studied. Red box is some with some detail of how the system works is known. White box with all detail of how the system operates are unknown. So they are based on defining the most important factors and through the use of observation, measurement, experiment, and statistical technique, connecting them to soil loss. So defining the objective. So model necessity, simplification of reality. So decision need to be made on a suitable level of complexity or simplicity depending on the objective. The starting point for all modeling must therefore be a clear statement of the objective. The starting point for all modeling must therefore be a clear statement of objective. This may be prediction or explanation. So for the managers, planners, policymakers require relatively simple predictive tool to aid decision making, while the researcher seeks model to describe how the system functions in order to enlighten understanding of the system and how it responds to the change. This chapter is concerned only with predictive models since these are most useful for practical application, but Increasingly, many of these models are developed by researchers and have a sound physical base affecting our knowledge of how the emission system works. Decision. So the objective has implication for how well a model must perform. Scaling models are simple in concept and designed to define problem areas. Usually, it is sufficient in prediction of the order of the right order of magnitude. Assessment model need to predict with greater accuracy because they are used for rating the salinity erosion. So the model should be formulated conceptually, representing by a flowchart such as shown in figure 6.1, something like this. Viewing the model in this way enable the structure of the system, the logical order of transfer of energy and matter through the system variable, and the interaction between the variables to be defined. Empirical model. A lot of models. Therefore, we can switch to it. Because this book provides example as well for the model, how to use it. But for my slide, I'm only focus on USLE, universal soil loss equation. So the simplest model is a black box pipe letting sediment loss and runoff. The relationship is US equal to A Q to the power P. So this is a black box, means input and output only. US is the sediment discharge and Q is the water discharge. It is not always possible to establish the value of A and B with confidence. The relationship between sediment and water discharge may vary with the volume of runoff and therefore change seasonally. Um, so during the single storm, the value of the often differs on the rise of the flood wave from that on the recession. The main disadvantage of this type of model is that it is with no indication of why erosion takes place. Greater nesting of the cost of erosion is achieved by gray box model. So meaning input, output, and sum of the information between. This frequently culminate in expressing the relationship between sediment loss in a large number of variables with a regression equation. A problem with this empirical model is that the equation cannot be established beyond their data range, either to more extreme event or to other geographical areas. So it's limited to that data range and surrounding effect in the geographical areas. So the first attempt to develop a soil loss equation for areas such as hill, slope, and field was that of Zing in the 1940s. For related erosion to slope steepness and slope length. Further development led to addition of climatic factors based on maximum determined rainfall. That one is EI30. Crop factor to take account of protection effectiveness of different crop. A conservation factor, a soil erodibility factor. So changing the climatic factor to rainfall erosivity index R ultimately yielded the universal soil loss equation, USLE, in 1978. The equation is E equal to R times K times L times S times C times P, where E is the mean annual soil loss, R is rainfall erosivity factor, K soil erodibility factor, L slope length factor, S slope steepness factor, C is the crop management factor, and P erosion control factor. So since K represent mean annual soil loss per unit of RE and has the same unit as K, if K is in a ton per hectare for 1 unit of metric R, multiplication by the metric R value will give the value of E in ton per hectare. R is the rainfall erosivity index described in section 4.1 based on mean annual EI30. 30 refer to 40 days of rainfall. If E is in a foot ton per acre and I30 is in inches per hour, so R equal to EI30 over 100. K is the soil erodibility index, defined as a mean annual soil loss per unit of R for a standard condition of dry soil recently till up and down slope with no conservation practice and on slope 5, 20 and 22-meter length. K can be defined for a unit of both American and metric R wherever possible. K should be based on measured value if the value is obtained from the nomograph. Figure 3.1. Later we see the nomograph during the calculation. LS, the factor of slope length, L in slope steepness, can be combined in a single index, which express the ratio of soil loss under a given slope steepness and slope length to the soil loss. From the standard condition of a 5-degree slope, 20 meter long, for which LS equal to 1, the appropriate value can be obtained from nomograph or from the equation LS equal to that equation, where X is the slope length, S is the slope gradient in percent, as seen in section 3.3, the value of N should be varied according to the slope steepness. C, the crop management factor represent the soil ratio of soil loss under a given crop to that from bare soil. Since soil loss varies with the erosivity and the morphology of the plant cover, it is necessary to take account of changes in this during the year in arriving at annual value. So figure 6.2 give the typical range of value for different crops and management system. Key values for the erosion control practice factor are obtained from the table of the ratio of low soil loss, where the practice is applied to the soil loss where it is not, with no erosion control practice P equal to 1. Values cover contouring and contour strip cropping and vary with the slope steepness. P value. So problem we can fetch 133 prediction of soil loss using universal soil loss equation. Calculation of mean annual soil loss on a 100-meter long slope of 7 degrees on soil of the Rengam series. Rengam series is referred to the type of the soil under maize cultivation with counterband space at 20-meter interval near Kuala Lumpur, Malaysia. So equation is USLE RKLSCP plus estimating the R. In instance of locally published map of R value, 3 different procedures for estimating R from mean annual precipitation are used. So R is rainfall erosion index. So method 1 is mean annual to 695 mm from rows, mean annual rainfall erosion index Newton unit, information to NG, MM, HA, H, mega, gram, millimeter, hectare, hour. Is get number. Method 2 for Morgan wind erosivity with KE with energy more than 35. So yeah, 161,716. So multiplied by I30, use 75 millimeter per hour. It's no very recommended by some that derive the SLE equation at 20,187. The method 3 is from Foster, mean annual EI equal to 6 times P is 2695 times I30. So I30 is 75. You get 55786 divided by 100 to convert to this unit. So you get 55 and 79. So best estimate discard result from the method 3, which is rather low, 55. Take average value of method 1 and 2, 17,720. Estimating K soil erodibility index. So Whitmore and Burnham, this is the normal graph, figure 3.1. how to get the value of K. So from week 1, Benham, the soil have this is for Rengham series in soil, 43% clay, 8% silt, 9% fine sand, and 14% coarse sand content. When contains about 3% using the nomograph 3.1 with a first approximation K value equal to 0.005. One here, very small. Estimating LS. Slope factor for slope length and slope steepness S in meters and percent respectively. So LS equal to I over 22 0.5. You see the equation with control band of centimeter spacing I get centimeter as 12% approximation of 7 degrees. So 7 degrees equal to 12%. That one is can be referred to a table. So LS is 1.46. Estimating C, crop management factor. According to table 6.2, the C value for maize ranges between 0.2 and 0.9 depending on the productivity for many tropical farming conditions. C for maize lies within 0.4 and 0.9 depending on the cover. So during the 3-month period from seeding to harvest, the cover is likely to vary from 9 to 35% in the first month, from 55 to 93% in the second month, and 45 to 57% in the third month. Therefore, we might assume C value of 0.9, 0.4, and 0.7 for 3 respective months. So maize can be planted anytime in Malaysia, but assume planting after April rains, allowing growth, planting and harvesting in July and June and July, which are the driest month. Land is under dense secondary growth prior to planting, assuming C equal to 0.01 and allowed to revert to the same after harvest. Of the mean annual precipitation to 2% fall between January and April inclusive, 10% in May, 6% in June, so on. Assuming that erosivity is directly related to the precipitation amount, this value can be used to describe the distribution of the R factor throughout the year. From the above information, the following table is constructed. Table 6.6.4. So C value here coming from table 6.2. When we do adjustment factor based on the mean annual precipitation for Malaysia, then you get the weighted C value. So C factor for the year is 0.208. Summation of the this column. So estimating P erosion control factor, table 6.3, P value for control band equal to 0.3. So soil loss estimation, mean annual soil loss of E equal to 8.07 ton per hectare. So the NUSA soil loss equation was developed as a design tool for soil conservation training, but because of its simplicity, it have been made to use it as a research technique. The equation to purpose for which it was not intended, however, cannot be recommended since it was designed for inter-real and real erosion. Remember, real small channel. This should not be used to estimate sediment yield from drainage basin or to predict gully or stream bank erosion. Care should be taken in using it to estimate the attribution of hillslope erosion to basin sediment yield because it does not estimate the position of material or interpret the sediment delivery ratio. So you may refer to other type of model in the book. There are many type of model which include the method how to use it. I will quickly model chapter 6 modeling structure. Thank you.